We're going to talk about, again, some new concepts. And that's the concept of electrostatic potential, electrostatic potential energy, for which we will use the symbol U, and independently electric potential, which is very different, for which we will use the symbol V. Imagine that I have a charge Q1 here, and that's plus charge, and here I have a charge plus Q2, and they have a distance r apart, and that is point P. It's very clear that in order to bring these charges at this distance from each other, I had to do work to bring them there, because they repel each other. It's like pushing in a spring. If you release the spring, you get the energy back. If they were connected with a little string, the string would be stretched. Take scissors, cut the string, whoosh, they fly apart again. So I have put work in there, and that's what we call the electrostatic potential energy. So let's work this out in some detail, how much work I have to do. Well, we first put Q1 here. If space is empty, this doesn't take any work to place Q1 here. But now I come from very far away, we always think of it as infinitely far away. Of course, that's a little bit of exaggeration. And we bring this charge Q2 from infinity to that point P. And I, Walter Lewin, have to do work. I have to push and push and push. And the closer I get, the harder I have to push. And finally, I reach that point P. Suppose I am here, and this separation is little r. So I've reached that point. Then the force on me, the electric force, is outward. And so I have to overcome that force. And so my force, F Walter Lewin, is in this direction. And so you can see I do positive work. The force and the direction in which I'm moving are in the same direction, I do positive work. Now, the work that I do can be calculated. The work that Walter Lewin is doing, in going all the way from infinity to that location P, is the integral going from infinity to radius r of the force of Walter Lewin dot dr. But of course, that work is exactly the same, either one is fine, to take the electric force in going from r to infinity dot dr. Because the force, the electric force and Walter Lewin's force are the same in magnitude, but opposite direction. And so by flipping over, going from infinity to r to infinity, this is the same. This is one and the same thing. Let's calculate this integral, because that's a little easy. We know what the electric force is. Coulomb's law. It's repelling. So the force and the r are now in the same direction. So the angle theta between them is 0. So the cosine of theta is 1. So we can forget about all the vectors. And so we would get then that this equals Q1, Q2, divided by 4 pi epsilon 0. And now I have downstairs here an r squared. And so I have the integral now, dr divided by r squared, from capital R to infinity. And this integral is minus 1 over r, which I have to evaluate between r and infinity. And when I do that, that becomes plus 1 over capital R. Right? The integral of dr over r squared, I'm sure you can all do that, is minus 1 over r. I evaluate it between r and infinity, and so you get plus 1 over r. And so U, which is the energy, that the work that I have to do to bring this charge at that position, that U is now Q1 times Q2 divided by 4 pi epsilon 0 divided by that capital R. And this, of course, is a scalar, it is work, it's a number of joules. If Q1 and Q2 are both positive or both negative, I do positive work. You can see that. Minus times minus is plus, because then they repel each other. If one is positive and the other is negative, then I do negative work. And you see that that comes out is sign sensitive. Minus times plus is minus. So I can do negative work if the two don't have the same polarity. I want you to convince yourself that if I didn't come along a straight line from all the way from infinity, but I came in a very crooked way, finally ended up at point P, at that point, that the amount of work that I had to do is exactly the same. You've seen a parallel with 801 where we dealt with gravity. Gravity is a conservative force. And when you deal with conservative forces, the work that has to be done in going from one point to the other is independent of the path. That is a definition of conservative force. The electrostatic forces are also conservative, and so it doesn't make any difference whether I come along a straight line to this point or whether I do that in an extremely crooked way and finally end up here. That's the same amount of work.